Well, I will try to go back in time for these 10 minutes and start it. But I will take a couple of seconds of my own to remind you that a conference is finishing right now, and it's the best time to invite you to the next one, which will be not only for the Aharonov-Bohm effect, but for the related Berry phase that is only half as old as the Aharonov-Bohm effect. And both of them happened more or less in the same place, although I believe a slightly different building. But there will be a conference December 14, 15 at Bristol, and you are welcome. How good it will be, I don't know. Lev put the level of organization so high that it would be difficult to compete. But in any case, you will be most welcome, and let's see what it will come out. Okay. Now, hopefully, this will work. All right. So now let's go to the business. Dynamic non-locality and the Aharonov-Bohm effect. Well, this is the talk that was advertised, and this is the talk that I'm not going to give. And it is a very simple reason for that. Namely, Yakir told me that he would talk about it. So, okay, what can I do? In any case, let me just put things a little bit in the context to prepare the context for Yakir. As you all know, and in fact, as we heard in the first day of this conference, there are still plenty of fundamental problems in physics that are obvious, and people work very hard, and we don't know how to solve. And the most important of them is, without any doubt, quantum gravity. Well, it doesn't exist. It will be quantum gravity. And there are complicated things, and people want to go to 10 dimensions, or we don't know exactly to what. It is very important. It is very complicated. But if we think, if we compare with that what happens with the humble quantum mechanics, non-relativistic, very simple, trivially mathematical. Nevertheless, it is trivial only apparently, because the concepts behind quantum mechanics are, I think we can say, are not very clear yet. And the signature that they are not very clear is the fact that we always discovered new paradoxical effects in ordinary quantum mechanics. Why are they paradoxical? Well, they are not paradoxical by themselves. They are paradoxical meaning we do not have yet the deep understanding that will allow us to say, oh yes, that was obvious. Now, one of those examples, of course, is the Aharonov-Bohm effect, but there are many others. And for example, quantum information recently gave legitimacy to people to start thinking of the basis of quantum mechanics. In any case, just to put things into context, from what I learned working with Yakir, I believe that a deep understanding of quantum mechanics relies on, say, three great pillars. Three basic things that one should understand in order to really make a progress in understanding quantum mechanics. The first one is what I would call kinematic nonlocality, and some keywords are entanglement, Bell inequalities, and so on. Now, this is an area that at present is investigated very, very extensively. Again, quantum information gave legitimacy for this inquiry. But there are two others. The second one, in my view, is to look at pre- and post-selection. This is an idea invented by Yakir, in which he realized that in classical mechanics you can put initial conditions on a system, telling what happens at one moment in time. If you say everything about that moment, determines the whole history. Quantum mechanically, you can put two different boundary conditions, because a measurement that you will do in the future although you know everything that happened in the past, that measurement, you cannot say what outcome will be. You know probabilities, you don't know the outcome. Therefore, by seeing the outcome, you put a second time boundary condition. And the third one is dynamic non-locality, the subject I wanted to talk about. And this is related to the Aharonov-Bohm effect. Now, we've heard many absolutely wonderful talks about the AB effect. We saw experimental realizations. We see these beautiful interference patterns. Interference patterns that are intricate, they are, they are beautiful in a mathematical sense. And we also saw that these interference patterns are not only in quantum mechanics, but they appear in classical mechanics, as beautifully shown by Michael Berry. Well, this may lead us to think that, as a matter of fact, Aharonov-Bohm effect is very similar to what happens classically. It is nothing like that. The fact that you look at the interference and it looks like a classical interference is completely misleading. And the reason is that quantum mechanically, the wavelength is associated with momentum. And momentum is a conserved quantity. So whenever you will have this single particle interacting with anything else, momentum has to be conserved somehow. And the way in which it does, it is extraordinarily intricate. And this is one aspect that was realized by Yakir, I think in the 60s. But I believe this is the most important aspect of the Aharonov-Bohm effect. And, well, Yakir can contradict me later. But after I finish with this is just to prepare the framework for Yakir's talk. Let me go to the talk that I'm actually going to give, which is nothing as deep as the previous things, but it's just fun. Now, people told many things about Yakir, but there is one thing that you probably don't know. Yakir has a tremendous talent. Yeah, he has many, but this is one of them. Namely, the ability to almost completely avoid mathematics. So in my 5 years of PhD with him, the most complicated mathematical thing that I've seen him doing was a Gaussian integral. Well, if you think that's easy, it is not. Because what is replaced is trying to think physics and push the problem into a corner where the result becomes apparent. And doing that without throwing the important effect, to simplify, to press the problem to a point where the solution is obvious and you don't really need to do anything. So here is one of these ideas. The idea in this particular work, which was done many years ago, belongs completely to Yakir, and then many of us came and contributed, and we developed and found all kinds of aspects. But it is fun. And this is a paper that we know among ourselves as the paper of the 8, with Yakir, Sidney Coleman, Fred Goldhaber, Shmuel Nusinov, myself, Benny Resnick, Daniel Rorlich, and Lev Weidman. Okay, what's the question? Look, here I have one electron. It's a two-dimensional problem. One electron that is in a potential well. Suppose this potential well is infinite outside, so the electron doesn't leak. The electron is this yellowish stuff that is in. And here I have a fluxon, and I have a special fluxon. It is half a quanta of flux. Okay, so let's see. What do I know about this? If the fluxon does a small circle somewhere outside, well, nothing happens. So it collects a phase, and that phase is +1. If the fluxon goes around at a large distance, or in fact even close, but doesn't enter this region, it just surrounds the charge. since it is half a quantum flux, it acquires a phase of -1. By the way, here I move the fluxon, not the charge. It's the same thing if I would move the charge and not the fluxon. But since I'm talking about this big potential well, I find it easy to move the fluxon. Well, I'm not moving anything, by the way. Now the question is, what happens if the fluxon comes and goes through the charge distribution? Now, this is not exactly the scattering that was discussed in the Aharonov-Bohm paper, because here the electron is bound by the potential. It's a bit more complicated. Now, I will try to look at the problem in the adiabatic limit, when the fluxon moves slowly, 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 and when the electron is in a non-degenerate energy eigenstate. Well, if those are the conditions, and I move slowly and it's non-degenerate, by the time I come out, I do not excite the state of the electron. So the electron remains in the same state psi. All it can happen is to acquire a phase. The question is, what is the phase? Well, so here it is. If you go one way, it acquires a phase e to the I phi. By the way, it also acquires a dynamic phase, but that is trivial. One can account. If it goes the other way, it acquires a phase e to minus I phi. Okay, that's very simple. But this particular problem with half a fluxon has an interesting symmetry. Namely, it is time reversal. Let's see why. Think what happens under time reversal in the fluxon. Well, in the solenoid, you have a current that goes one way. If you do the time reversal, now it will go the other way around. That means that the magnetic field that was one direction now will be the other direction. So that means that the flux phi goes to the flux minus phi. Phi was half a quanta, so you get minus half a fluxon. But here's the point. Half a fluxon and minus half a fluxon, they differ only by an integer fluxon. And integer fluxons are unobservable in this situation. Therefore, the difference between one situation and the other is just a gauge transformation as far as we are concerned. So it has full time symmetry. And this happens only if the fluxon would be integer or half integer. So see the consequences. Just imagine that the wave function psi went to e to the I phi psi. What is the time reversal? I have to take the complex conjugate of the final state, so it is e to minus I phi psi star going to psi star. Okay. Now, here is one more ingredient. The function is, one can take a gauge in which the function is real to start with. And in fact, the fluxon is outside, so there is no problem with it. It's non-degenerate, it's real. So e to minus, so instead of psi star, I just have psi. So I can rewrite the second equation like that. And I can simply move the phase, start not with e to minus I phi psi, but psi, and move the phase on the other side. So this is the time reversed evolution, in which, remember, the fluxon doesn't go anti-clockwise, goes clockwise. But we discussed previously what happens when the fluxon goes clockwise, and that is, you have psi go to e to minus I phi psi, just because the geometric phase differs. From the last two equations comes out the fact that the phase can only be plus or minus 1. So we had the idea that as you go and you enter the distribution, you may surround a little bit of the charge, of this cloud of charge. So you might have thought that phi is something continuous and depends on how much charge I surrounded it. The result is no. the phase cannot be anything intermediate. Can be only +1 or -1. So let's see what is the consequence. Think first of this circle. The trajectory outside doesn't touch the cloud of charge. Phase is +1. I start entering, it's +1. It is +1. Some moment, if I go all the way around, it must be -1. So at a certain moment, the phase must jump. I can now start taking a trajectory and deforming it a little bit. Go from a small circle to a big circle just by making infinitesimal changes. At a certain moment, when I made an infinitesimal change, the phase must jump. So that happens there. Okay, even more dramatic, what that means, consider first a trajectory that goes below that point and now one that goes above it. They compensate all the way outside, and all that remains that little circle. So that means I have this potential well, I have an electron in it, everything is nice, continuous, beautiful. Nevertheless, there must exist a point that if I go with a fluxon infinitesimally around that point, the fluxon will acquire a phase of -1. Well, would you believe it? I made just a tiny, some people believe me. Well, I don't know. There are some possibilities. Either they don't understand what the problem is, which is possible, or they already know the answer. I believe it's the second. Okay, so what is happening? How can a wave function that is so continuous, you do an infinitesimal change, and completely you acquire a phase of -1? There is a dramatic change there. Well, there is one possibility. And that possibility is, if you recall, just to see what happens, that I can interpret, at least formally, an Aharonov-Bohm phase as a Berry phase. And we know that in some instances, Berry phases jump. When does that happen? If there is a degeneracy. But there was no degeneracy. I just claimed I'm looking at a situation where I start with an electron in a non-degenerate eigenstate. Otherwise, the whole idea is not correct. So what is happening here, what must happen here, is that the moment if I come and I put the fluxon at that particular point, I induce degeneracy. Somehow I force the system to become degenerate. Well, let's see a particular case. See if this is completely crazy or not. Consider a problem with spherical symmetry. Now, if there is a point where this thing happens, it must be in the center. That's a good guess. Well, we know what the eigenstates are. They are states of angular momentum, m0, m1, m2, m3, and going one way, m-1, -2, go the other way. Now, instead of moving and putting a fluxon into it, let me just start with zero magnetic field in the middle and start to establish a fluxon. What happens when I increase the magnetic field? I create an induced electric field, so we'll start giving a kick to the electron. All of those that moved in one way are pushed now to move faster, so they go up in energy. All the eigenstates that were moving opposite are now slowed down. So at a certain moment, they hit each other. And suppose I started with a ground state that was non-degenerate, it now hits another eigenstate, and they become degenerate. So it means that is a forced degeneracy. The amazing thing, though, is that imagine any potential that you want. No symmetry whatsoever. Yakir's argument is that there must be the case that for this most general potential, there exists one point, well, or an odd number of points, that if I would put half a fluxon there, I would produce degeneracy. Okay? How does that work? Well, everything was continuous to start with. A nice, beautiful, quite regular wave function. But I start now and I put a half fluxon. The half fluxon is here. What happens, you can show immediately, that the half fluxon induces a place where the wave function now must be 0. So there is a line of 0 emerging from the half fluxon. How can I prove that? Well, it's pretty easy. Go, for example, to any singular gauge that you want. Take it on a line. In that case, the Hamiltonian is real, and all this singular gauge does is forces psi to go to minus psi when you cross the line. Well, if here the function is positive, the phase is positive, here the phase is negative, it must go through 0. There are many other ways of proving this. The upshot is, it doesn't matter how you prove. You can change the gauge, you can change whatever. The fact that the wave function is 0 there, that is an observable thing. So when you put a half fluxon, the wave function changes dramatically. Well, it may change a little bit when I just enter, and then it is a short line of 0. And see what happens now when I go with a fluxon around this singular point. What must happen is that this line of 0, the wave function deforms, and the line of 0 just goes around and pushes the charge completely around the fluxon. And you get a -1. Or alternatively, if you just entered and came out here, the charge is pushed away, so nothing goes around the half fluxon. The phase is +1. What happens if I come and put a half fluxon exactly at the point of degeneracy? Well, for spherical symmetry, there must be two solutions, orthogonal, and here there are the solution. It's quite trivial. They are orthogonal. But of course, it has symmetry. So you may imagine there must be a solution where the line of 0 goes this way, or that way, or that way. Well, you can obtain all of them by superposing these two different solutions with real coefficients. Okay. Just to see, here there are 3 eigenstates without half fluxon. This is the ground state. This is a state of superposing m equal +1 with m -1. And here is superposing m equal +1 with m equal -1 with a minus sign between. And they have lines of 0 crossing them completely. Yes? It's exactly like you would have for a particle in a box. In the first excited state, it has a 0 there. If I put a half fluxon, the situation must change. Because now it's just a line of 0 emerging from the semifluxon. So this is a situation, that is a possible situation, the third one. How do I get from one to another? Well, just imagine that I start with that state and I introduce half a fluxon. A line of 0 will trail from this half fluxon. And when I push it to the middle, I obtain this eigenstate. Here it's more interesting. If I push half a fluxon along the pre-existing line, what must happen is I annihilate the line. By the way, lines of 0 cannot just disappear. They are topological. Okay? The only way they can disappear is if the wave function in a whole region will become 0, which is really, it's not going to happen. So you must just introduce another topological object that will do the job. Here, well, when you start introducing the half fluxon, the pre-existing line of 0 will get deformed, and in the end you get to this situation. I said there must exist one point that if you put the half flux on there induces degeneracy. In fact, there can be an odd number of points. Why odd? Because if I go around each of them, the phase jumps from 1 to -1, and when I go around, I need to get an odd number of points. A bit more fun. Consider an arbitrary potential well with an electron, and suppose I already inserted here, I inserted in it some half fluxon, these 3 of them. And now I come with a fourth, while I maintain the 3 half fluxons fixed. Now this problem again has time symmetry, so exactly the same arguments apply. So it must be that in the presence of these 1, 2, 3 half fluxons, there exists at least one point, P, where if the fourth fluxon comes, the phase will jump. And by the way, from the pre-existing half fluxons, from each of them there must be a line where the wave function is 0. That could be a line from the half fluxon to the outside world or connecting two half fluxons one to the other. Let's play another game. Suppose a spherically symmetric potential, and I introduce half a fluxon over there. Now, according to what I just said, if I take another half fluxon, there must exist a point where if I put it, I induce degeneracy. 1 minute. No, 5. You took 10. But I will try to shorten. Now, what is fun about this situation, what does the location, the center of the charge mean? Well, that is a shadow fluxon in the following sense. Suppose I move now this charge distribution while I keep the two half fluxons at the distance that I just discussed. Now, when this charge distribution comes such that its center surrounds that point, it will accumulate a -1. Why? Because when the charge was there, it was a degenerate situation. So now you have like an Aharonov-Bohm in which this big atom that you may imagine, this cloud of charge, goes and picks a phase of -1 when it surrounds a shadow. And that is the shadow over there. In fact, by symmetry, there must be another shadow over here. Now you may ask, what happens if I move the half fluxons closer to each other? Well, if I move them closer to each other, the shadows probably will come close. But if I move them even closer, the shadows must disappear. How do I know that? Well, if I would put the two half fluxons one on top of the other, they would be an integer flux, so no phase whatsoever. It means if I separate them a little bit, there shouldn't be any effect. So it must be the case that the two shadow fluxons came, hit each other, and annihilated. That was a two-dimensional situation. One can do a three-dimensional situation. This big blob is this cloud of charge, and I have a fluxon of some arbitrary shape. It is half a fluxon. And now suppose that I'm looking for a one-parameter curve. For example, I fix the orientation of this thing, and I only allow it to move rigidly, or whatever I want to do. Again, if I just go outside and I don't encircle, phase +1, a big tour, the phase -1, therefore it must jump. So there must exist a location for any sort of curved fluxon that if I put in there, degeneracy will occur. Well, just to make Mark happy, I can stop here. There are many, many other things that one can play with. The next one is, for example, to talk about a triple degeneracy and so on. But here is what you can do just by having a good physical intuition, no mathematics, and, well, just to play with it. Thank you very much. Well, I don't want to speculate what would have happened if the number of authors would have decreased by 1. we know we got to another paper. Okay, there are many other aspects. Obviously, when the fluxon enters the cloud, it changes the energy. Therefore, there must be a force acting on it, which is highly non-intuitive because the Aharonov-Bohm effect in general doesn't require forces. And how does the fluxon do? Well, the fluxon changes the phase, and now the electron has to interact in a different way with, say, the potential that doesn't allow it to enter. Out of these two, very interesting effects appear. So now the fluxon may be either absorbed into or may be repelled from the charge. Well, we don't know. Well, we know some of the things, but most of them we don't know. And in fact, we have no proof that degeneracy will occur in a mathematical way. But we can.
How old is this result?
Not as old as me. I don't know, 80, well, 90 probably, something like that. 92, no, sorry, 93, 92, something like that. Okay.
I know this is the adiabatic approximation, but if an observer is on top of this moving flux, okay, you can see the electrons moving slowly inside the magnetic field.
They don't enter the field. They don't enter inside the fluxon.
No, if the fluxon enters inside the space where the electrons are, so they touch each other.
No, they have, I forgot to say, but as in all these Aharonov-Bohm things, you put also an infinite potential along the line of flux so that they do not enter inside the magnetic field.
You don't have to do it by itself.
It does by itself, but okay, well, let's put it.
Any understanding on what the behavior of the electrons will be in the framework, in the frame of reference of the fluxon by this property?
Galileo will tell you. You go and ask Galileo.
Thank you, Pavel. Well, it depends on your definition of what do you mean by understanding. We know some of the things.
Well, on this philosophical